high-performance computing and its applications. So we have the speaker for the day. So Dr. VSM Srinivasa Verma, sir has joined us kindly for taking a session. So Dr. SM Srinivasa Verma has completed his BTech ECE from JNTU, Kakinada in 2013, and sir has an MTech Electronic Systems from IIITDM Kanjipuram. And then sir went on to do his PhD also in IIITDM itself. So sir has completed his PhD in 2021. And when he was doing his PhD itself, sir had been doing a graduate teaching assistant. So sir was working as a graduate teaching assistant in the department of CSE. Then he served as a research assistant professor in the School of Computing, our SRM IST Kartangulattur. So from that, sir had joined Shivanadar University as an assistant professor in the Department of Computer Science and Engineering from June 2023. So that's sir's journey. So sir has got over 2 years of experience in teaching, and his area of specialization is placket classification, IP lookup, network intrusion detection systems, like that. Sir has published several papers in ACM publications, all from ACM publications, and sir is the recipient of a Best Paper Award in the conference, in the international conference organized by our Ministry of HRD, by all IITs. In that, sir has got a Best Paper Award in the year 2020. Okay, so welcome, sir. Hearty welcome to our So now our HOD ma'am, Dr. S. Prasanna Devi ma'am, will give a memento to sir.
Once again, thank you very much, sir, for accepting our last minute invitation. Thank you. Dr. Noor is unable to join us today because he had some other personal commitments. So, sir has actually immediately accepted our invitation. So, thank you very much for that. And morning, I was not able to join. Thank you.
So
there's some faculty board meeting going on. So I'd like to thank Bharati ma'am for taking today morning session. And I thank both the coordinators of Atal, coordinator and co-coordinator. They're actually the two leaders who are effectively running this show for the past 6 days, and today's a successful 6th day. Thank you very much for being very so present. Sir will deliver a short session about the applications. We have requested him to cut short his session. Sorry for that, sir. And after that, we'll have a short valedictory wherein they have selected the best participants. Dean will join us and he'll give away the best participants award. Thank you.
Thank you, ma'am.
Information in a very eager way that applications alone. So excuse me if there are any repetitions. I think you might have learned a lot of things in this over last 6 days. If there is any repetition, excuse me. I'll just
we'll consider it as a summarization of that.
It is summarization.
Yes,
okay, thanks. So yeah, so by now most of you have understood what is HPC. Its primary objective was bringing in multiple smaller computational nodes, making them coordinate with each other to solve computationally intensive tasks, right? So the reason why we need to bring many smaller entities together, any idea that you got in this over this last 6 days? What is the major motivation in bringing them? In 2003, the processor manufacturers has observed a syndrome called as power wall syndrome. So after scaling up the frequency of even if you see in 2003 when Intel released their processors, in 2003, their clock frequency was around 2.5 gigahertz. Even today, the processor clock frequencies were only 3 gigahertz. So it looks like there literally has been no advancement that has been made over the last 20 years. No, that is not the case here. Actually, as per the power laws, the power consumption, if I can, yes, it is directly proportional to the cube of the operating frequency. So when it starts exceeding a certain level, like let's say Intel experienced this power wall syndrome at 3.5 gigahertz, when they increased the processor clock frequency beyond 3.5 gigahertz, they observed that the heat dissipation coming out of the processor is more than, or it is almost equivalent to the power that is coming out of a medium scale nuclear reactor. So running processors is not at all feasible at such high frequencies. At the same time, the computational requirements are also growing up. So what came as a solution to this issue was, let's not get into that uncomfortable zone. Let's not take the processors to that uncomfortable zone where they experience, significantly superior or damaging level of power dissipation. Let's limit them in their comfort zone and let's have multiple smaller processors. Let's distribute the power consumption across multiple smaller processors. The major motivation for going for HPC was actually the power wall syndrome that happened in the year 2002 to 2003. So we all know this. They are there for accelerating the work, okay? And then we have this notion called cluster, where we bring in multiple nodes together. Again, we know that node, by now we might have understood the node is a combination of multiple cores, and we just insert multiple nodes within a rack, and this combination of racks forms our supercomputer, okay? So there are multiple modes that we do, ways we leverage this. The very basic way that we can do on a laptop level on multi-core processors is our OpenMP, okay, and MPA. And when we have this SIMD kind of problems, especially all your image processing kind of problems, single instruction, multiple data, we get into these graphic engines, okay. So the major issue here was the this is how the way that they tackle this problem is using these clusters where there is one master computer. Don't worry, I'm going to get into the applications. I've taken two use cases apart from image processing, or sorry, typically non-ML, non-AA problems. I have taken one application in computing, so I'll just talk about them. So this is, have you studied about any particular supercomputers in this?
Summit, Frontier.
Yes, yes. So you know how they are organized, right? How the supercomputers are organized. So what is the main thing inside a supercomputer? What do you treat the main core element inside a supercomputer?
Accelerators.
Accelerators and
Switches.
the network switches that makes the data transmission, the resource sharing among them. So unless we have the right kind of network switches, the switching fabrics, the right kind of switching fabrics, the data transmission is incomplete within them. So and they bring in the major latency. Okay, so this is the case even in majority of the supercomputing applications, unless and until we restrict the data accesses when we are launching the threads on multiple cores and all. So one disadvantage that everyone will get into is, unless and until they restrict the total number of memory accesses to L2 cache and L3 cache and the main memory, so the supercomputing power we cannot leverage, because the way the processor operates at is around the core or the any supercomputing core, it usually operates at a frequency of 3 gigahertz. But if you take the speed of a main memory module that we use in our laptops or the best module, that has a maximum clock frequency of 1.5 gigahertz. So there itself we have 50% speed difference between them. So unless and until there is the right kind of network fabric that is in place, so this particular power, the complete power of this multiple cores cannot be leveraged, right? So inside a node, you must be aware what is there, right? Inside each node, okay. So these are the, so which operating systems this HPCs typically use? 99% Linux, there are very specific cases where people use Unix operating systems, right? So how do you measure the performance of an HPC? Flops, right? So what is this flop? Floating point operation. So how do you measure? This gives us some overview, right? So you are all aware of this? Yes. Right. So if you look at the gap in the kind of supercomputings that are being in place, okay, the gap is superior except the first 5 supercomputers. So the red line, if you take, right, the blue line is the combination of all the computational power when they converted them into the p flops, okay, the petaflops. Their combination of the top 5 supercomputers in 2014, as of 2014, was that, okay. But this red line is only the combination of the top 5 supercomputers in place. So the majority of the supercomputers are highly concentrated, okay. And one interesting thing is, even though this supercomputing falls in our computing domain, so the amounts of the total percentage of applications for which they are being deployed is very less in the core computers area, correct? They find their major applications in the areas that are other than the regular computer science. So the major applications we can see in computer science, even though we call them, we use them in genomics kind of areas, they are also not related to primarily to the computer science. The primary areas of computer science was our A and ML fields. Apart from that, so the majority of the applications that are highly reliant in uh, on HPCs are this regular basic sciences fields. So the main reason was, one is laws of thermodynamics, the first and second law of thermodynamics, and the Boltzmann equation. Or almost all of the astrophysics subjects and all of this cosmology related subjects, astrophysics, they study about the star formation, cloud dust formations, and how the fission and fusion reactions that happen over in our galaxies, okay, so which resulted in the formation of these various stars, okay, Milky Ways, etc. and all. So in this thing, the major cause and response behavior is captured by a well-known equation called as Boltzmann equation. And Boltzmann equation is an order 5 level dependent equation. So simulating Boltzmann equation was never a reality unless until 2011, when the supercomputing power was started leveraged. Okay, so this HPCs found some significant applications uh, in the area of this astrophysics, okay, cosmology, etc. And these are the libraries. Of course, all of us know this. We know how much important they are. Even like we might have used this NumPy, SciPy, and we can also leverage the Google Cloud capacities, right? So when we are executing them, so there are multiple libraries beyond our AML libraries. So I hear that you've already studied the parameters of these supercomputers. So these are the domains where we can, okay, you can, these left side ones will be the non-computing applications. I'll just talk about one or two of them in the coming slides. In our computer science, I have just one question. Where do you find the applications of high performance computing apart from AI and ML? Any one area, one domain? Genome sequencing, pattern matching. Pattern matching, I mean, there are two ways of doing pattern matching. Okay, I'm concerned
For
about
pattern
it.
matching also we make use of AI and ML only.
I'll just show you that as well. Not necessarily. There are two directions to that. Okay. Yeah. Network routers. So we all connect ourselves to internet. Okay. So the entire all these computers that are in this lab will be aggregated at one point that we call it as our Ethernet switch. So this we call it as a small lab. This entire lab is a smaller lab. Okay. Now there are multiple such LANs in this entire building. Okay. So all of them separated by their own network switches, and all this network that are connected to these LANs will be connected to one router. That router we call it as an enterprise router. That enterprise router belongs to this organization SRMIST Vadapallam. Okay. And whatever packet that goes from all of us, all of these hundreds or thousands of users, has to go through that one router alone. That we call it as an enterprise edge router. That is this organization's router. And that router will be connected to, will take the packets from here to the ISP provider through optical links. All the backbone links are optical links. Right? So now, that ISP is not there to provide the internet to just this one organization. There will be hundreds of such big scale organizations which which this ISP is going to provide its service. Right? Now, assuming the speed of this organization or the total speed that this organization subscribed to was around some 4 Gbps or 5 Gbps, assuming the ISP is providing services to some hundreds of organizations, what do you think is the scale of data the ISP service provider has to handle? Maybe I would say some 100 or 200 gigabits per second. Right? Now, if we go back to our computer networking basics, what is the average size of a packet inside as per IPv4 protocol? Maximum packet size 1500 bytes. It is limited by the Ethernet frame size. But that's not the case. Usually, the studies reveal that the average packet size that is traveling across internet will be somewhere between 200 to 250 bytes. Now, simple mathematics, if we divide 1 terabyte, so the ISP is handling 1 terabytes of data per second. Why? It's an aggregate point of multiple organizations. It has to handle the traffic of multiple organizations. If we divide 1 terabyte by 250 bytes, you tell me what will be the count? It will be anything not less than 50 million packets per second. Right? 50 million packets per second. So now, an organization, okay, or the ISP service provider has to handle 50 million packets per second. So what do you mean by handling here? Each packet comes from here to there. Based on the kind of packet, it has to do the routing decisions, and it also has to do some security inspections as well. So all these things are some computationally intensive tasks. So if you can just do that simple mathematics, it turns out that each packet gets hardly 10 picoseconds time at the ISP service provider level. An ISP service provider has a maximum of 10 picoseconds to take some action on the packet that comes to it from various organizations. If at all it goes beyond that, if the service provider cannot honor that packet within the stipulated time, what happens was that packet, the entire speed of the network will come down. Right? So now this is one side of the story. So on the other side, the story was the users expect more from the modern routers than just forwarding. Modern routers does a lot of functionality for us. One is firewall inspection. Okay, one case was firewall inspections. The second, deep packet inspection, you might have studied somewhere. Deep packet inspection is inspecting each and every packet payload for any possible virus patterns, presence of virus patterns within them, and so on. All these things are carried out by modern routers. So this entire, I just took this example. Uh, this entire, these are the 4 significant steps that each and every router has to take care of in the process of handling a packet. One thing is, once the packet reaches the core router or the aggregate router, it has to do the parsing. Each packet has header and payload. Not every component in the header might be useful for processing by the router. So parsing means extracting only those fields of interest. Okay, and then comes the major task, that is classification. For example, once the packet reaches the router, there might be a different. These modern day ISP service providers, they use an terminology called differentiated services. Depending upon the kind of charge they charge from the user, the treatment to the packet belonging to that user will vary. Okay, some packets from some users will be kept on some high speed links, some packets will be on the regular lines, etc. These are called as differentiated services. So how do they know whether this packet is belonging to a privileged user or a normal user? So they have to look at some fields within that packet. What are all the typical fields they look at? Destination IP addresses, source IP addresses, port numbers, etc. All these are the fields that they use. Now, how many users or how many organizations, the traffic pertaining to how many organizations this particular ISP service provider is handling to? Hundreds and hundreds of organizations. Now, so to classify these incoming packets, he has to define some predefined rules which are dynamic in nature. Okay, some predefined rules he has to take. Okay, and then subject each rule, he has to do a comparison of each packet, incoming packet, against these thousands and hundreds of rules. Okay, within the stipulated amount of time, and this comparison outcome. Okay, based on this comparison outcome, an action will be taken on the packet. The action can be anything. If it is a packet from a privileged customer, give it a preferential treatment. If it is from a normal customer, don't give it any preferential treatment. Put it on a regular line on its way to the actual server where it is planning to go to. Okay, or if this is a packet having some threat inside it, just drop that packet. Don't divert it to the server. Or if it is a packet targeted towards DDoS attacks, okay, do the tracing back. So these are some of the actions that will be there that the router needs to think about while handling every packet. Once that is done, editing means these are the things, and then the packets are forwarded accordingly, a decision. Now what is the challenge? So this is how the rules will look like. So you can say enterprise 1, E1 stands for enterprise 1. The enterprise 1 can be our campus, SRMIST. Enterprise 2 can be some other campus or some other tech park, can be enterprise 2. ISP service provider, ISP 1 can be the BSNL network. So that guy can be then Airtel 1 and that guy can be anyone. So the point is, these are the things we call as edge routers, the circular ones, the cylindrical ones. Okay, so they are going to enforce these kinds of policy decisions upon the packets. Alright, these are the ones that are going to enforce the policy decisions upon the packets. So they can do packet filtering. That means, for example, there is any billing issue, they have to deny all the traffic that is coming from ISP3 that is destined for E2. Right? So there will be some rules that are sitting here on X, okay, which identifies the packets from ISP3 destined to E2 and block them and just drop them. Other one is policy routing. If at all some packets are coming from certain ISP, E1 to E2, just transmit them on some high priority links. Let us say they have subscribed for some voice or IP links. Voice always needs high speed data links than data. So Give them some priority. The third one can be accounting and billing. You need to keep a count on how much amount of data that has been originating from E1, so that at a later time you need to bill them. So traffic shaping. So these are some of the applications. The one which I haven't shown is the firewalls, etc. Here they also falls under the same domain. Now, what's the challenge? The computational challenge. So, to present the use case for HPCs, we look at the computational challenges in what? So, you look at that number 5,000 to 10,000. They are the sizes of the typical rule sets that sits on any typical edge router. Okay, any typical edge router, there will be rules. The total number of rules will be somewhere between 5,000 to 10,000. And it will be larger. The maximum size can be as high as 1 lakh. Okay. Now you take the case of an OC 768 link. OC is an it's a standard that governs the kind of backbone link speeds. In India, we deploy 40 Gbps link speeds. OC 768 denotes 40 Gbps. OC 192 denotes 10 Gbps. Now the European backbone networks are with 100 Gbps. They are migrating to 400 Gbps. In India, from 40 we are on our way to migrate to 100 Gbps. Okay. Now a backbone link having 40 Gbps speed can carry in the worst case 134 million packets per second. Now imagine 134 million packets per second reaching a router, and you have to compare each of that packet against 5,000 rules. And each rule is not a single dimensional rule, it's a multi-dimensional rule. It's going to be a multi-dimensional rule. Because based on just one field comparison, we cannot take a decision. Sometimes you need to drop certain packets accessing certain applications. All of our organizations do have firewalls in place. So how do you detect a particular person accessing Facebook which is banned inside an educational organization? Based on the destination port number and the IP address. So destination IP address, these are the two factors. And let us say in the same organization, access to Facebook is allowed for faculty and it is not allowed for the students. Now how do you differentiate between students and faculty? The source IP addresses, right, etc. So each rule is a combination of multiple dimensions, and you have such 5,000 or 10,000 of such rules. So this becomes a classical case of multi-dimensional search problem, which we always see in machine learning. But we have better algorithms. Machine learning always presents some sort of some chance for error. But in packet classification, you cannot afford for any error because network security is given utmost priority. Okay. So now this is a classical case of intensive computation. So but what happens if the ISP service provider fails to do that in real time? Okay, fails to honor this speed requirement, the network traffic speed will come down, or else it may intentionally skip some packets from inspecting and just forward them. One disadvantage, if you are not having that capacity, but if you still choose to do that, you will network the speed limit. You will limit the network speed. That will make that creates a bottleneck in the system. Or else, if you choose to skip inspecting some packets because you are not capacitated to do so, so what you are going to do, you are going to compromise on the actual functionalities. So the major objective is high-speed packet classification. So you can see this 8 Gbps one is the one that pertains to one heuristic based very popular decision tree called as hypersplit. This we did on this experimentation, the basic supercomputing experimentation. We did on just excuse us, we haven't actually did any parallelization. We did it as such in the supercomputing platform that was there in AAATM Kanchipuram. It is only just in 4-node system. Each node is having 16 node system. 16 node. So the maximum threads that you can bring in was maximum of 50,000 threads that you can bring on. But we haven't parallelized anything. We just implemented to see that. So the maximum speed that anyone can guarantee was 8 Gbps. Whereas the required speed was around 40 to 100 Gbps in real time. Okay. So how do people do them in reality is they use specialized engines, hardware engines, based on built out of some VLSA hardware chips. They use. They are not going to rely on software. Wherever in computer architecture, there is always one thumb rule that whenever you need speed, avoid software presence as much as possible. The presence of software will automatically reduce the speed. That's the thumb rule. Okay. So bring in hardware. When the hardware comes into picture, the things become faster. So what they do was, this is the case where your question, the pattern matching question, will also be answered. So there are 2 dimensions to the pattern matching. One, you can do it as a machine learning level, where you will always build some model, and any pattern that will fall in that model or out of that model. Especially pattern matching in network intrusion system detection, they uses only the anomaly studies alone. Okay, they build a model out of their patterns. Whether the incoming one is fitting that model or not, they will never go on doing exact comparison. Okay, but exact comparisons are important when you need, especially in areas where genome sequencing is present. Even today, for genome sequencing and all, exact models are in place. Actually, they rely more on exact models. Actually, okay. Now, what do they do? So you have to do a comparison of some millions of packets against multi-dimensional rules. So if you bring in software, what is the simplest algorithm that can come to our mind? Linear search. Again, that's not scalable. So we use an engine where we just take the input from the packet and we give it to a specialized hardware where there are some parallel circuits, okay, with some the rules are stored in the hardware, and this packet, when you feed it as an input to that, it does a comparison in parallel and gives you the output in just order one time. Order one again is a misleading term there.
Sorry to interrupt. So all the comparisons can be done without the software. Even.
Yes, I think so. I think I took away that slide. Yes, without the software. So this is your processor that is present inside your router. It takes this is the switch fabric. It takes the packet inside it and it does the parsing, the step I have told you there. Parsing means extract the necessary fields and give an input. So you have a parallel memory here. Okay. Now once you give, if there are 1000 rules, all these 1000 rules will be compared in parallel with the input. That's the parallel memory. So the ternary content addressable memories. Why ternary? Networking though we have don't cares. Class A. The first octet is binary. The rest of the 4 octets are don't cares in class A. Correct? Class B, class C, and then we have CIDR routing, etc. So networking, there is you need to store don't cares also in networking. So ternary means 0, 1 and a don't care. Until now we have seen only the memories which have zeros and ones, binaries. Our RAM, our cache memory, etc. can only store zeros and ones. But in networking we have a third case called as a ternary, because our entire networking works on prefix level. What is that prefix? Class A means 8 bits are the prefix, 24 are the don't care condition. Class B, class A. Of course, we are no longer using classes, but we have CIDR routing in place even today. Correct, right? So that is the case that they store in parallel and you do a parallel comparison. And it tells us which is the matching rule and it gives it back. But if you only do this entire functionality here itself, it takes us a lot of effort. So actually results at least show that these devices are able to deliver you a classification speed anything not less than 50 Gbps, the hardware devices. Whereas the software maximum limitation is 8 Gbps. I'm talking the non-HPC cases. Okay, non-HPC cases we are talking about. And but even though we have solutions in place, those solutions are extremely tricky. Why? This is a hardware device. Let's say, yes, we have an AND gate IC which we teach to our students. Okay, let us say we have a 2-input AND gate IC. Now the other day we need to show a 3-input or 4-input AND gate IC. That IC can we configure? No, we have to throw it and buy some new IC and bring it in. Okay, that's the issue with hardware. Hardware is not at all flexible, just like software. Okay, with the emergence of new protocols each and every day, okay, when I want to make this particular hardware unit feasible for emerging protocols, no, it will not, because it's a fixed structure. It has its own limitations. On the other hand, I can just change my decision tree algorithm. The hypersplit is a very popularly known algorithm. I can just update that algorithm to suit for the additional dimensions, etc., etc. But then they have the major bottleneck is they cannot scale for the speeds. Now, this is the case where this supercomputing came in handy. So there was one switch, the G switch. G means graphic switch. That was actually, this is based on a research article. So OpenFlow is the new protocol on which the software-defined networking switches are based on. The entire SDN is based on the entire software-defined networking is based on one key functionality that's called as packet classification. All that classification which we have discussed so far, it is that. The dimension, the comparison problem is a 12-dimensional problem in OpenFlow. There are 12 fields and thousands of such rules. Every time you have to compare each and every incoming packet and then take a decision. The advantage of SDN is it offers runtime reconfigurability of the network. Okay. Now they have used a simple NVIDIA GTX 580 GPU, again acceleration purpose. So it is having 24K threads capacity. You can execute 24K threads by accordingly configuring the stream multiprocessors. Okay. Now by linear search here, I'm talking about 8 Gbps. Okay, I'm talking about 8 Gbps alone by using advanced data structures. Okay, tailor-made heuristic-based decision trees. Okay, but here I'm using a simple linear search. Okay, which has been launched in a multi-threaded manner, and the throughput that they are able to derive is 20 Gbps. And the second thing is the $2,000 cost is almost comparable to this hardware cost that comes, and the system is not big either. The graphics card size is limited. Only thing that you need is to supplement with sufficient cooling fan mechanism. That's it. And anyhow, all the routers in this organization, if you look at the core router room or in any organization, they are only in air conditioned environments. So that should not be a thing. And when they used decomposed searches based on Bloom filters, etc., the speed is scaled to over 40 Gbps, whereas the same linear search cannot even exceed 1 Gbps on any multi-core platforms. So that's one classical case beyond AI and ML where this high performance computing comes in particularly handy. Right? Similarly, I have only talked about the header inspection part alone, but deep packet inspections means you have to inspect the payload as well. So the payload has Snort is an intrusion detection system, open source software, Snort SMORT. It's very popular. Whatever research that any person does relies upon their open source databases. When they release, they keep on updating their databases once in 3 months. The total threat patterns in the latest Snort database was 60,000 patterns. The size of each pattern will vary from as small as 32 bits to as high as 1670 bits each pattern. The size. There are 40,000 such or some 60,000 such thread patterns. So each packet payload, you have to take each byte and see whether it is matching with any one of these actually, right? So even in that cases, actually it's not prohibits from using this AML based algorithms. Okay, because 100% accuracy is needed when it comes to threat detection. When you go rely on any kind of ML model, the false positives and false negatives are inevitable. So one thing that that actually being deployed in places, this Bloom filters based pattern matching. Okay, right? So this is one thing, and the other case which I have taken was the NWP from Earth Sciences. Actually, ESS is an organization that provides that solutions for numerical weather predictions. Okay, so but these small scale solutions, right? So yes, these are some of the solutions that are being adopted here, right? So numerical weather prediction means it's a form of most popular form of weather prediction which gives the exact numbers as an outcome. The 24 degrees on tomorrow, okay, the amount of humidity that is going to be there, etc. All these things they're going to provide it in numbers, okay. So and it is most widely adopted, okay. So the numerical weather predictions is based on the physics laws, okay. The considering the today's parameters and all, they rope in complicated equations, okay. So now this numerical weather predictions, they rely mostly on the HPC solutions, okay, for giving out the exact weather predictions. So this is inevitable. These kind of solutions are inevitable in almost all the. This is the one in BWD, Bangladesh Weather Department. Okay, so these are the places where the HPCs are being deployed in real time, right? So, and this is one of the popular software grid analysis display system. Okay, so without HPC, they are not able to visualize it. Okay, because no, when it comes to the image processing with respect to weather prediction, right? So the area to area, there will be boundary conditions. They define boundary conditions from area to area, and simulating them in real time is a computationally intensive task. So with the help of HPC, they are able to solve them, and they are able to depict this kind of pictures. And this software can run only on an advanced HPC system, not on any other computers. Okay. So
Are
this
there
is
any open source version of these kind of applications will be available?
ma'am, this particular thing which I have discussed here, this is thoroughly open source. Open flow, SGL are completely based on open source. Yeah, nuclear reactors. So the main issue in the nuclear reactors is they rely mainly on the Boltzmann equation. Boltzmann equations, computation using Boltzmann equation is a very complicated task because of its order 5 level dependency. So modeling, I think in 2014 or 15 for the first time, France started deploying HPC systems for simulating their nuclear reactors. They cannot blindly scale up the system. They have to do this CFD analysis, the computational fluid dynamic analysis, okay, to analyze how by increasing, by scaling up the nuclear reactor power by just one unit, how the reactors will respond to that. All these things, they only first they need to do simulations, and then only they can go for the real-time testing with some certainty. So this is where HPCs comes in really handy, and these are and the analysis done by this NIH of Britain in calculating the total number of contacts in COVID, second wave and all. They are based on, again, they made use of this HPC systems. These are some basic things which I've modeled. So these are not into my domain, so I have only touched them. Only place where I worked little bit was in this accelerating the routers using this.
Thank you very much.
Yes.
So you were saying, sorry sir, I catch only a bit of it. So is it like you were real time, you were looking at the header of the packet?
Yes,
IP
it should
packets?
happen in real time.
So that is why you are saying that prediction will not work out. We have to do an exact match.
Exactly. I know people do recently with ML and all, people do work on papers with respect to doing packet classification using AI and ML. But if you see, none of those papers are in any IEEE transactions because they really know that it is not an appropriate solution. They can publish that, but not in the right way.
So what exactly we would be looking at in that header, sir? Address
Header-
alone?
No. Destination address, IP addresses. Destination IP, source IP.
So we will have a blacklist, whitelist kind of a thing, and then look
Yes,
at
yes, yes,
blacklisted IP address. So we will do an exact
Not
match, something like that.
it depends on that. Some firewalls, no, they uses default allow rules.
Okay.
Default allow. That means then you have blacklisted rules. If the packet is within matching with any of these blacklisted rules, then only block it. Else allow every other packet. Or else the default deny rule. Yes. So that is the whitelist rules.
So earlier also we were doing this kind of packet filtering, right? But you are saying that HPC we are able to do it on a
Requirement actually. The thing is, the scale of rules that are gone up, like this OpenFlow thing came in 2004. When OpenFlow came, the file earlier we used to do only the packet lookup on one dimension, routing. Only the destination IP will do, and the next best hop decision will take. So that's a single dimensional problem. So that too, the number of rules will be 1000 or 1500. So they used to use the tri data structure. So that was never a big issue. But when this OpenFlow came, the problem dimension has increased to 12 to 15 dimensions. So not just destination IP, we look at the source ID of the MAC, source MAC, destination MAC, and frame type, source IP, destination IP, source port, destination port, ingress port, egress port, type of service, all these fields for every packet. Again, is thousands of such rules. Each rule will have the components for all these folders. So it becomes a computationally intensive search problem. It's a search problem. It's not any computational problem, but the search is a complicated search.
so the HPC does it in a very
Yes,
fast real time.
exactly. And this entire search problem falls under it's a classical example of SIMD, single instruction, multiple data. Everything, the instruction is single, the comparison instruction.
But different kinds.
Yeah, if it is a destination IP, it's a longest prefix match. Yeah, so the kind of thing. So it falls under SIMD. So it presents an opportunity for scaling up. And again, these HPCs cannot be used on simple routers like our lab things. There we have limitations. But if they are core routers, like this campus will have only one core router. The router which connects this campus with the ISP service provider. So in these core routers, these HPC solutions can be deployed.
So that means that routing protocol or something has to be run on HPC or something like that.
These particular functionalities which are computationally intensive, if they are run on this HPC system, they cannot become a bottleneck, provided if you are trying to scale up the speeds.
Thank you, sir. Just looked up some of it. That is where you have published papers. I think.
Yes.
Thank you, sir.
Yes.
So please be seated. I will.
Yes, no. I would not say the research was not there, but you cannot show me a single.
The feedback link for both the
IEEE
sessions is posted, please fill it.
Because IEEE transactions, they look at the real world significance before accepting. So I can show you the right type of things. Yes. They can do it. It's a very good idea. But the thing is, you see now, what they do, they build a model. Okay. They build a model. See, there are two types of intrusion detection systems. Pattern matching based intrusion detection system. Second one is anomaly based intrusion detection system. Pattern based, no AML will be used. Okay. In anomaly based models, they build a model and they see whether a packet is
There's a request for conducting free workshops as a part of this training what they have done through AICTE. They can go to 5 different colleges within the radius of 100 kilometers and they can train your students as well as conduct faculty development programs. If there are any requirements in your own institution, kindly send us a mail so that both of them are HPC trained trainers, right? So they'll come and address it.
And I also thank all the participants here.
Yeah, that is the most important thing. Thank you. So you have to go back to your own institutions and give this knowledge back to your students. That is the ultimate aim of this FLFT. Thank you, participants. On behalf of SRM, I'm saying a big thank you.
Thank you.
Thank you.